Okay, so we'll start shortly. Let's just try to do this. And have the video. Okay. Yeah. Okay, so let's see how it's working. So just let me know if you can see what I scribbled today. So what we have to do is finish a little bit about LAG2, and we will do lag X 1 and 2. So this is what we want to do today for this class. So let's see. Okay. Okay, well, let me know if you read and hear properly. Yes, the idea is that on Thursday we do some exercises. That's depend on the week. Say this week it's a little bit special because remember it's the first week, so we are adjusting a little bit. We don't have that much material cover yet. So we do some exercises, but we have also to finish some of the theory part. In particular, we want to be sure that we are comfortable with the vector product. So I start by writing down some property of the vector product, right? So we didn't meet yesterday. That's the idea, right? So what we do today is see the formula for the computation of the vector product. So we finish speaking about vector product. And I recall you the basic properties. We saw about the vector product of vectors. So say we have u, v, and z, and then we have some c scalar. And then we want to speak about property which we call linearity. One, so quick remainder, it says that you can take out the coefficient. Then we have the second part, which is linearity 2, which tells me I can split over the first factor. And then we'll have skew symmetry, which is telling me how to split over the second factor if it is what I want to do. And then we have the skew symmetry, which is telling me what happens if u cross v is compared with v cross u. And we saw that this has to do with change in orientation. So the verse will be exchange. So we will get just a big minus in front of everything. And finally, we have something telling us what's happening if you compute the cross product of a vector with itself. You get this zero vector. Now, the most difficult to prove is this linearity 2. For the case of the scalar product that was done with projection, if you remember, if you read the notes, here requires a little bit more. So out of the remaining three, say 1, 3, and 4, is there anyone you'd like to see together? We'll cover also some of the exercises, yes. So Beatrice Tomatis, to see linearity 2, we need to introduce the box product, so which is what we are going to do next. So it is something else. And what we can do is use these to derive a general formula to compute the cross product, the vector product formula that probably you already know from some of your previous study. So let's just give an example. So say we want I plus j, and we want to cross product these with k, just to see what we get. Quick exercise. Yes, this is just to recall them. Yep. So to have a starting point in which we all agree on something. So as a quick exercise, can you tell me what is the answer here? So what is this cross product? So a few minutes for you to think about this. So we have a suggestion, j plus I minus j plus I. Well, let's do that. So the idea is I want to use linearity. In this case, I use linearity 2. So I get I cross k plus j cross k. And then clearly we have to remember how to compute the basic cross product among the unit vectors, I, j, and k. Okay, so what do you do here? Well, we know what the process is. When you have to compute, for example, I cross k using the definition, we know that this vector, I'm just going quickly here because we already know, will have the direction of the common perpendicular. So this is the direction. Also the magnitude of I cross k, we know this one. Can you tell me the magnitude of I cross k? Yes, it is 1 because it comes from the magnitude of I, magnitude of k, and then the sine of the angle, which in this case is this angle here, which is pi over 2. And so it is a product of three numbers 1. It means it is 1. So I cross k is a vector having this direction, having length 1. So it is either j, or what could it be? Well, could only be the opposite. So can only be here, length 1, but opposite verse. So we have only to decide which one of the two is. And how do we decide that? Well, the right-hand rule. So since the first vector is I and is going over k like this, you have to put your right hand in this precise way. And so this is the verse you get. So what is the conclusion? The conclusion is that the first summand is not j, but it is minus j. Plus, and then you have j cross k, which in this case is just I. And this is how we get the answer. So one of you, I think, produced it correctly. It was Sofia Carnau, she said minus j plus I. And exactly here is what it is. So this is using linearity 2. Using linearity 1, you can also take away coefficient. Using skew symmetry, you can split over the second vector. And using property 4, you can get rid of products of vectors which are parallel or like that equal to themselves. This is what you use to produce the probably well-known formula for the computation of the cross product in components. So how do we compute the cross product in components? Well, say we have U, and in components it is Ux, I, U, Y, J, U, Z, K, right? And then we have, say, W, Wxi plus Wyj plus Wzk. And then we want to compute U cross W algebraically. So without using the definition, but using the properties. I know this vector will have three components, something times I, something times J, and then something times K. It is convenient to have a minus here. So the rule is nicely expressed when you have a minus in front of the J component. Yep. And then you write down the components. Now I write them down and then I show you a mnemonical trick to remember that. So start writing down. So I is multiplied by U, I, W, Z minus U, Z, W, Y. Then J is multiplied by U, X, W, Z minus U, Z, W, X. And then K is multiplied by Ux, Wz minus Uz, Wx. Here is the formula. How do you prove it? Well, you prove it by applying to this product linearity 1 and linearity 2. So you take these gentlemen and you multiply by 1, 2, and 3. When you multiply the first one by the first one, you get 0 because they are parallel. When you multiply the first by the second, you get I dot j, which we know is going to be k, and so on. The minus here is to make the formula look better. And if you are patient just a second, Claudio A, you will see what you get. Is J and K the same? If it is, I made a stupid mistake. And thank you, I made a stupid mistake. Sorry. Yeah, that's my fault. So let's put this in red so we can see it's different. It is UXWY and it is UYWX. Thank you for noticing. Nikola Stankovic, thank you. And I was telling you, how can we remember these in a compact way? Well, there is a trick coming from matrices. So now it's just a trick. What you do is writing down a table in which you use UX, UI, and UZ, and then WX, WI, WZ as rows. That's what we learn to call a matrix. Then when you want to look at, for example, the I component, you forget about the first column. And what is left, you treat in this way. That's a rule, determinant computation. You multiply these two, and you see them here, UI, WX, and then you multiply these two, but you subtract them from what you had before. So this is a mnemonical way to remember how to do using determinant of 2 by 2 matrices. So probably you saw them and then you know how to proceed. If you never saw them, well, it is a little bit more mysterious, but it will be clear in the not so distant future. If you want to get, say, K, for example, well, then you forget about the third column. So to get K, you forget about the third column of the matrix. So let's say, just to do this, let's copy it, put it here. If you want to get K, you just forget about the third column. And then you repeat again, multiply ux wy, and then multiply uy wx, but subtract. Okay. Samuele Cravero, the minus is a part of the proposition. You don't want the minus there, simply you put a plus and then you exchange these two. So there is no explanation, but it is a definition. A further explanation is going to be that when you compute the determinant of a 3 by 3 matrix, you have alternating sign. So if you know 3 by 3 matrices, it will be clear. If you don't know 3 by 3 matrices, it is just coming from this proposition. If you want to see why you have the minus, simply you have to go and see when you get J multiplying an element from here and an element from there. For example, UXWZ, Simone Cravero, if you want to see this in this way, UXWZ come in this way, right? But if you multiply I and K, you don't get J, you get minus J, right? So this is why you have the minus, because when you compute, you get it. Of course, you can put a plus and change the sign of what it is inside. Okay, before that, Mohamud Yahya Ali Hassan says, I calculate I star K by right-hand rule, but I get opposite signs. Well, if you are the only one getting opposite sign, Mohamud, probably you made a mistake. My suggestion is write down your computation on a piece of paper. You can send me a picture by email and we can discuss it, okay? But you know, if no one else complained about that, it's an indication that there is some computational mistake on your side, right? And here you see, you have to compute I vector K, and that's not J by the right-hand rule, because it's not K going on to I, because K is the second vector, if it helps you, okay? Okay, so final thing about the dot cross product. Remember, the dot product, the scalar product, we could use to compute orthogonal projection. Here, we can use the vector product to compute areas. So we have a proposition, and here it comes. When you have two vectors, say U and W, I can look at them, even if they are free vectors, I can imagine to apply them to the same point. And if you do this by magic, you see that there is a triangle appearing, right? Here it is. Here is the triangle, call it T. Well, what happens if I compute the cross product of U and W? This is a vector, so I can take its magnitude, and this is a number. And this number is just twice the area of triangle T. So the magnitude of the cross product is just twice the area of the triangle, which sides are U and W. Very quickly, sketch of the proof. Very easy, I think. Well, what is happening here? You have your triangle. Put it here. And let's see what we can do with this triangle. Well, if I want the area of the triangle that I see here, what I need is to multiply height by base. So the area of the triangle I know is 1/2 the base length, magnitude of view, times h. But how do I compute h? Well, we know very well by basic trigonometry. If I know this angle here, h is going to be hypotenuse times sine of the angle. So this is going to be 1/2 magnitude of u, magnitude of w, sine of alpha. So this is how you get h. And if you just go and have a look to the definition of the cross product, this is the magnitude of u cross w divided by 2. And so this is why we get this nice relation for the area of a triangle, which means that if you are in 3D and you have a triangle in 3 dimensions, you can easily compute the area of the triangle, making the sides into vectors and computing the cross product using the formula that we described before. Okay, to finish this discussion, we'll speak about mixed product in a second, but let's see if you have questions or doubts about what we said up to now, or if everything is okay. Okay, probably everything is okay. There are no questions or doubts. Good. So the next and final step to finish LAG2, the file, is to speak about what is called the mixed product of vectors. So mixed product. So the ingredients for the mixed product are 3 vectors. So we give a definition. So we take 3 vectors, say u, v, w, the mixed product of these 3 vectors in this order is u cross v dot w. So look, you compute the cross product of these 2 vectors, which is indeed a vector, and then the dot product of 2 vectors, right? This one and this one there. So in the end, you get a real number. Okay, so in the end, you will get a real number as a result of the mixed product. The mixed product, so, is a real number. And we would like to know if this real number has some meaning or not. Keep in mind that the mixed product is also called box product. And this means it has something to do with the with some box. Sorry, I'm looking in the chat because there was something. So Jorge Miguel Ignacio says, is it commutative? Well, that's a nice question, which we will address in a second. But you know, commutative, usually you have 2 factors. Here you have 3. So I have to interpret what you say. So you say, if I exchange the order, does the result change? Sometimes it does, sometimes it doesn't. we can explicitly say when it does and when it does not. And we'll see in a second. However, when it changes, it only change for a sign, cannot change too much. Cannot change too much. Okay, so here is the proposition. So the proposition says that the absolute value of the mixed product is the volume of the box, which we call parallelepiped. I will say of edges U, V, and W. So what do we mean by this? Well, here is the meaning. You have your vectors. So here is U, then here is V, and then say here, maybe here is W. And then if you remember, we can make, so for example, here there is a parallelogram, right? Given by the first two. And now this parallelogram, you can slide, if you want, up and down. So I'll try to do that. You see, you can slide. So I'll try to make this, I'll try, dynamic. You can slide the parallelogram from its original position up, 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 up you go, and then you stop when you reach the top of the arrow. If you do that, you will span a box. So here is the box. Here is the parallelepiped. And this parallelepiped, this box, B, will have a volume. And what is the volume of the box? The volume of the box is the base area, which is some number, which multiplies the height of the box. Okay, so the base area, hopefully, let's see if we can make anything nice here. The base area comes from these, is the area of this parallelogram, right? While the height, bear with me, the height is how you go from here to the base orthogonally, right? So that's the base area, that's the height. Okay, so what do we need to do now? Well, we want to compute the base area, for example. And I have a trick for computing that. If you compute U cross V, what do you get? Well, I get a vector Z. A vector Z, which is doing what? What is this vector Z? Well, this vector Z is orthogonal to the base of the parallelogram. And can you tell me what is the magnitude of Z? So let me know, what is the magnitude of vector Z? What do you think? Is the area of the base, because if you divide by 2, is the area of the triangle. If you don't divide by 2, it is the base area. So the magnitude of Z is the base area. And if you note, Z is parallel to the height of the box, right? It is parallel to the height of the box. So the box has not height W usually, because W is not orthogonal to the base, but Z is. So note that Z is parallel to the height. So how do I produce the height of the box having Z? What would you do from W to produce the orange part, knowing that the orange part has the same direction of Z? Well, Z is not the right magnitude. Z is as long as the base area. That's not the height. Yeah. Orthogonal projection. W usually is not in the same plane as U and V. It is in my picture because I'm making a two-dimensional picture, right? But it is not. So to produce the height, what I do is the following thing. Let's say the height as a number is going to be W dot Z. So this is a number, and that's what we get by multiplying, but we said we need the orthogonal projection, right? And this is what is happening when you do this kind of process. You get the orthogonal projection. So what is the conclusion about the volume? Well, the volume, oh, sorry, this is just to be, the dot product could be negative in the case Z is pointing down, right? So we want an absolute value here, otherwise it's not working. So the volume of B in the end is going to be what? We said W, so absolute value of Z, and let me write this Z.W because so we don't have to change on the top, sorry. So it is U cross V dot W. So this is what we get in this situation, right? This is what we get in this situation. And here is the volume of what we want to produce. Okay. Let me read in the chat. So there are questions about this. And there are questions about the height. We said to compute the height, we do the orthogonal projection. So the vector height comes from the formula we saw last time. So the vector height comes from the formula we saw last time. And then we multiply by vector z to get the final answer. So I see why you are confused. That was a little bit too quick. So let's say we introduce an orange vector here. So orange vector, probably like this. Let's see. Yep. And this orange vector, I call, say, h with an arrow. Okay. So I want to get that. So h is the orthogonal projection of w along z. So it is w dot z, z divided magnitude of z square. So this is the height, right? This is the height of the box. And what is the magnitude of the vector height? So what we call height. So height is w dot z in absolute value divided by magnitude of z. So this is the number we are looking for, because this is the orthogonal projection of z, of w on z. Okay, so this is what we have here. Okay, now let's go to what we want to compute, okay? So I want to compute the absolute value, here it is, of this. So I want to compute the absolute value of this part here, u cross v dot w. U cross v dot w. And let's see what is this. This is, we said, vector z multiplied by w, right? So this is what we want here. Vector z multiplied by w. Dot product, sorry, and then we break the absolute value. Then I explicit this. This is the magnitude of z times the magnitude of w. And then in between, I have the cosine of alpha. What is alpha? I have to go here for a second. Is the angle in between z and w. Is the angle in between z and w. So it is here. Okay. So let's take the picture with us downstairs for a second. So here is the complete picture. So what is here is the what we call height. This is what we call height if we put the absolute value, you see the absolute value which is here, stays here. And so this is the height. Otherwise, could be minus the height. And then I'm multiplying the height, h, by the base area. So I did base area times height. And this is volume of the box. I hope it is clear now. Okay? So look at this formula. This is what you want to compute. This dot product you write using z, which is this vector product. Then you have the product of the magnitude, cosine of the angle, and this absolute value has nothing to do here because this is positive, so goes there. And this makes this part here, you see, W cosine gives me actually H, because H is what you get on this side. The absolute value makes it positive, multiplied by the base area, you get the volume. If you remove this absolute value, what can happen is that this cosine can be negative if the z, is pointing down, for example. So you will not get the volume, but minus the volume. Okay? I hope it is clear. It's always difficult to make these three-dimensional pictures, but I hope it is clear enough. Just a quick note. Let me write permuting U, V, and W, the sign of U cross V dot W can change. But the absolute value is the same because it's the volume, right? Volume is the same, no matter, is always the same. So for example, if you take V cross U dot W, this is minus U cross V dot W. And then you can try exchanging also V and W, but the answer is going to be always either plus or minus the volume, okay? The lesson will be recorded, yes. I think, because while speaking, I realized that the easiest way to understand is to take the formula, split it like this, realize this is the base area, and interpret this one. Interpret this one as hypotenuse times cosine of the angle, which gives me the height of the triangle. This picture is a little bit misleading because Z looks like the height. So probably I should make the picture a little bit different. So I'll say Z could be much longer than the height. But when you make the orthogonal projection, what you are getting is just the height. You are just getting H, okay? So three-dimensional picture can always be a little bit confusing, I know. The magnitude of Z is the base area because that is the formula of what we saw before, right? Triangle. So what is this one? This is magnitude of U, magnitude of V, and then you have the sine of angle, call it beta, which is here, right? So when you do V magnitude times sine beta, you get the height of this triangle here. You see this triangle. V sine, you get the height, and so you get the area of the parallelogram since there is no half in this part, okay? Okay, then there is a nice question. When is it going to be 0? So let's see how you answer that question. That's a very nice question asked by Sayed Mustafa Sayedi. So let's make a note about it because it's interesting. So U cross V dot W is number 0 if and only if. Let's see how can you conclude these one. Someone says when there is no height. So it basically means when the volume of the box is 0. And when is it the case that the volume of the box is 0? Well, in some sense, when there is no box. Yeah, I think we are almost going there. So, but you can just think about when you get your Amazon box and you flat it to throw it away. Basically, you make one of the 3 sides, edges. So this is one edge, second edge, and this is the third edge, say U, V, W. When you crash the box, what you do, you take this edge here and you push it down. You squeeze it, you put it there, right? So in the same plane. So exactly, Davide Cutorti, that's the final answer. Basically, you say, if and only if U, V, or W are coplanar. And this also includes the case in which one of the 3 is 0. Okay, so exactly that. If and only if they are coplanar. Coplanar means, this word means lie in the same plane. So the plane where the box has been squeezed. Okay. Good. Any question about this before we go on? Can you show the example of coplanar? I'm not completely sure. I'm not completely sure of what you mean, but let's say a very simple situation could be take V, U, and W like this. This is I, this is J, and this is I plus J. So if we make a 3-dimensional picture, right, in X, Y, and Z, I can put the vectors. So this is where V is. This is U, and this is, how can we make it graphically appealing? Probably like this. And this is W. So this is, we said V, U, W. So there is no volume because they are in the same plane. And if you compute it, try. That's kind of fun to see if you compute I cross J dot I plus J, right? What do you get? Just do this computation for me and then we'll see. What is the answer to this computation? Yes, we can do that. Yeah, it is 0. And why it is 0? Well, because we know from the meaning of the box product. Exactly. The fact it is 0 comes from the fact that this is K. And you see K is sitting here, so is orthogonal to W for sure. And when you do the dot product, you get number 0. And what is important, and you can see here, is that this is not changing if I do I plus j cross, say, j dot I, or if I do I cross I plus j dot j, because I'm just permuting, I'm moving them around, the answer will not change. Okay, then since someone asked, I said this can be used to prove linearity too. Okay, so let's make a quick note. Box product can be used, and it is done in the notes, to prove linearity too. So it can be used to prove linearity too. And I just give you a suggestion. There are two proofs of this in the notes. Linearity too basically is to prove that if you have the sum times the third, this is equal to u cross, dot z plus v dot z. And to prove that this is equal, I hope you agree, it is equivalent to prove that the difference is 0. So this is equivalent to say that the difference is 0. So someone had a smart idea to say, well, I give a name to this vector here. I call it t. So what we want to prove t is 0. And to do this, we prove that t dot t is 0. Why is this useful? Because if you take this expression, you dot product it with itself, you use property of the dot product that you know you can split along the sums, and then you will see, you will use the property of the mixed product that basically is written here, that you can exchange the order of the factor without changing the final answer. So if you're interested, you think it's very good idea to go and read it in the notes. So you see how the mixed product, the box product, can be used to prove this, okay? Paolo Lovera, because keep in mind, this is a proof. So you need to devise a way that produce the final result you need. So if you want to prove that a vector is 0, one way is to prove that the dot product by itself is 0. Because you see, this is true if and only if t is 0. T is the 0 vector, sorry. Oh, also here there is an error. Okay, because when you take the dot product of a vector by itself, you always get, oh no, I see what you mean. I'm so sorry. No, that was a mistake. Oh, I see. No, these are cross. No, that was nonsense. Oh, I see. No, that was complete nonsense. Thank you. Now I realize. Yeah. Oh, that you don't do. That was a mistake. That you don't do. I thought you were asking about why to use the other part to prove, but no. Your question was more precise. I made a mistake. Okay, so I suggest we do the following thing. We take 4 minutes break. So we come back at 12:30. And so we can have half an hour of exercises. Some of you already asked some exercises from the sheet. So we can go and see them. Okay, so take a few minutes break till 12:30. Okay, good, good. Okay, so I just answer to some of the question in the chat. Here it is a dot product, yes, because if you put a cross product of a vector by itself, it is just 0, right? So that's the first thing. And this is number 0, while this is vector 0, because this number here I hope you remember, this number here is always the magnitude of t. So it's not necessarily 1, someone asked, it's not necessarily 1 if t is not 0, is the magnitude. But the fact is that the magnitude is 0 if and only if the vector is 0. The unique vector with 0 magnitude, the 0 vector, right? That's what we said. And yes, Taham Masp Tariq, he gave the right answer to the question. Good. Okay, so now we move to the exercise sheet. And there was a question about one specific question, some vector equation. I see one. So this is number 7 here. And it is x cross j dot k, which we want to be what? Number 0 or vector 0? What do you think? Is it number 0 or vector 0? Yes, it is number 0. Exactly. So, and say I want to solve this one. Solve this one means the usual. Find the vector x such that this happened. Giuseppe Falcone, this is a kind of treasure hunt. You have to go and look for it, but it is not hidden very well. There is a place on the pagina del corso where all the material is well placed, and you should go and look for it, because otherwise you miss also the lecture sheets and so on, right? So Materiale is a good place to look for that. Okay. What do we do now? We want to solve it. How do we solve it? We want to find x. How do we find x? Well, there are a few ways in which we can do this. So say one way is to say, well, x is a vector, and ijk allows me to write all possible vectors. So it's going to be something like ai plus bj plus ck. So if I want to do this, I will have to go back in the expression and substitute these x. And of course, now to solve, I have to find a, b, and c. Okay? So we need to go and find a, b, and c. And to do that, we have to compute. So let's do this together. So I place everything inside. So ai plus bj plus ck. Then I do cross j dot k. However, this one I don't like much because I don't like to compute cross products. Maybe you do, I don't do like them much. So I know that if I just shuffle everything to the left or to the right, it is the same. Okay? So I just shuffle left. So I move everything to the left. So you see this one goes first position, this goes second position, this goes out, and so comes back from the third position. So we don't need to compute the big cross product, just one. Then there is a question, I don't understand why is X. Well, that's some basic starting point. When you want to represent any vector in 3 space, you use a basis. This is what we will learn how to call it. This means that you look for X, whatever it is, it will be given by 3 components. So you get a component along parallel to I, component parallel to J, a component parallel to K. How you find this component? Well, that's another part of the story that we can also discuss if you want, okay? And so I decide to represent it in that way, okay? Perfect. Then there's a question. Amos Lanzuisi says, can only change in sign is not necessarily going to change in sign. For example, if you exchange the first 2, the sign will change, but that's not a shuffle. Shuffle means the first goes to the third position, the second goes to the first, and the third goes to the second. It's just sliding everything, okay? Also, keep in mind that since we are looking for equation, you know, this is 0, if and only if this is 0, no matter if there is a plus or a minus 1 here, okay? However, I will tell you more about the shuffling business. And I'll do it here. So let's put it here. What do I mean by this shuffling business? I mean this. I mean that V1 cross V2 dot V3 is equal to V3 cross V1 dot V2, which is equal to V2 cross V3 dot V1. This is if you shuffle, right? And you can also shuffle left, which means you just read backwards. So these are all the same. That's what we mean by these shuffling. So 1, 2, 3, 3, 1, 2, 2, 3, 1, right? If you exchange, for example, 1 and 2, then you will get a minus. So, for example, here, I will get minus V2 cross V1 dot V3. But this is going to be equal to, this is going to be equal if I keep shuffling. So this is equal to, if I shuffle now, I move everything to the left, this is going to be minus V1 cross V3 dot V2. And this is equal to be minus V3 cross V2 dot V1, and so on. I hope it is more clear now. So let's read. Yes, Sayed Mustafa writes the formula. Amos Lanzui said, if I exchange first and third vector, what is going to happen? The sign will change, or am I wrong? Someone says makes sense. So we when we shuffle, we can do every combination except we change the number of the vectors product. Shuffle is a kind of permutation. It's called a cyclic permutation. Then there are permutations which are not cyclic, and then things can go in a different direction. And then you have to see what will happen. So if you want to predict this carefully, well, you compute the box product, and then you see if you get plus or a minus. What I'm saying you here, I hope this helps. So when you do this shuffling process, basically you are rotating the box. So this is rotating the box. And so nothing is going to change. The volume is not going to change, and not even the sign. What Amos-Lanzouisi suggests is not a rotation of the box, it's a symmetry operation, and then there will be a minus. However, what I'm going to tell you is if you want to derive these properties, you just need to compute the mixed product explicitly, and you will see what you get. It's a good exercise for you to try, and then you let me know what you get. So Amos-Lanzouisi, please take some time this afternoon, exchange them as you please, and then try to predict what happens, try to work out a rule, you send it to me, and then I tell you what it can be, okay? Okay. Shuffling makes computation easier sometimes. Someone suggests another way of computing this. Yes, there could be many different ways of computing this. You can decide to use the one you prefer, to choose to follow the one you prefer, as long as you follow a procedure, there are no mistakes, everything is going to be fine. Okay, so now instead of J cross K, I know what I have to put. I have to put exactly I. Okay, and so I have I dot what is here. And so the answer here is going to be A. So our conclusion is that this is true. So the equation is satisfied. Oh, sorry, this is not what I meant to do. The equation is satisfied if and only if A is 0. So if and only if X is of the kind Bj plus Ck with B and C real numbers. So there are infinitely many solutions, and they are all possible vectors, linear computation of J and K. Yes, it is any vector in the x equals 0 plane, if you see what I mean. Okay, I was looking in the chat, but it looks like you are answering and making question. Can we say x is 0 vector also? Well, if you take b and c equals 0, x you get, for x you get the 0 vector. Yes, shuffling in this case made computation easier, property of the box product. But as I told you, you can solve it also in a different way. I can imagine at least one different way, and probably there are many. So another way of doing this could be to say, well, look at the equation. So let's look at the equation. Here it is. And just rewrite the left-hand side using shuffling again. Oops. So we said this is equal K cross J. Oh, sorry. That's wrong. It is equal to J cross K dot X. And we want this to be 0. And we know what is this. This is just I. So we are saying I cross X is 0. And you can give a geometric interpretation on this one. So you just want all vectors having 0 orthogonal projection on the vector I. So X, well, probably X is not a good name. So say this is I, this is J, this is K. So this is vector I, and you look for all vector X having 0 orthogonal projection. So where are they? Well, precisely here, right? This is the plane, which is orthogonal to all of them. It's the complete plane. I just highlight that area to make it easier to read. Okay. So hopefully this was helpful. Okay, so this was the exercise called 1.7 in the notes. Is there any other exercise in the exercise sheet you want to have a look at so we can do something you're interested into? The second one. Okay, so the second one is about computing areas. So the second one is about having 3 points, A, 1, 2, 3, B, 4, 5, 6, and C, 7, 8, 9. Then there is the triangle T of vertices A, B, C, right? And then there are a few questions. So is T equilateral? Is T, well, let's do like this. So it is equilateral, isosceles, right angle. So this is the first group of questions, say. And then what else? And then there is a question 1 and question 2 is about perimeter and area of T. Okay. Well, oh, okay. So this one is not interesting for you. So you want to see, you said, number 10. And the other one was number 5. Okay, so let's start with number 5. And then we see how much time we have for number 10. Okay, so number 5. Well, so we can have a look to this quickly and then move to number 5 or 10. Okay, so this is the triangle. Okay, given by vertices. So we want to use vectors to do our computations. So the idea is that you have to produce vectors from your data. So there will be a vector here, and a vector there, and a vector here. So these are the vectors we can have a look at. So for example, let's say I focus on these vectors here. So U and V, for example. So what is vector U? Vector U is the vector going from A to B, also called B minus A. And this is a vector having I, J, K components that come from the components of A and B. And the idea is that you take subtraction. So the coefficient in front of I is 6 minus 3. The coefficient in front of J is 5 minus 2. And the coefficient in front of K, well, sorry, I read from left to right instead of from right to left. Anyway, the coefficient in front of I is 4 minus 1. The coefficient in front of J is 5 minus 2. The coefficient in front of K is 6 minus 3. Okay, so we get 4I plus 3J plus 3K. This is U. What about V? Well, V is, same process, is AC or C minus A. So the coefficient of I comes from looking at C and A. So it is 7 minus 1, 6. The coefficient of J is 8 minus 2, 6. The coefficient of K is 9 minus 3, 6. So here it is. Yep, sorry, this is a 3. 4 minus 1 usually is 3, right? And these are the two. For example, using these two, we can immediately find the area. So the area of T we can immediately find as the cross product. So I can say that the area of T is going to be U cross V, and then absolute value, sorry, magnitude. But just take a look to the vector that we are looking at now. Well, I hope you see that they are special. So this is 3 times I plus J plus K. And this is 6 times I plus J plus K. So they are parallel, and so the cross product is 0 because they are parallel. Because U is parallel to V. If you don't realize that it is 0, oh, thank you, twice the area is this number, and the number is a number, is not a vector. And the reason why it is 0, it is because they are parallel vectors. If you don't realize it, what you do? Well, if you don't realize it, what you do basically is go and compute the cross product using the table. So you write 3, 3, 3, 6, 6, 6. But then when you use it for the formula to find the coefficient of I, J, and K, if you remember, to find the coefficient, for example, of I, you multiply these two and subtract. So you get 18 minus 18. And then you get again 18 minus 18. Even if you have to put the minus in front of it, well, nothing is going to change, and you get 18 minus 18. So in some sense, since the area is 0, this means that the triangle is degenerate. So it is a degenerate triangle? Well, what happens basically is that these two sides are not like in the picture, they are parallel. So what happens in reality is that here is U and here is V. And so the third side is going to be even on this line too. So there is actually no triangle. And so all the other questions are kind of fuzzy. That's the purpose of the question, to make you realize that things can be weird sometimes. Okay, there are only 3 minutes left. I think it's a good idea to call it a day and say that we meet again next week. So you can prepare for your next lecture, and I can do the same too. Any quick question you want to have answered now? Does it matter where to put X, Y, Z? No, it does not matter, but usually people do the way I wrote it. So X is like in the plane. Usually X is the horizontal and Y is the vertical. Carnot theorem is also called the cosine theorem. So in this context, it is giving you the length of an angle, so a side, using the other two. So here it is. Yep. I will upload. The Telegram for the moment is only for me to tell you what is going to happen. Yes. That's the idea. It is too confusing if you write me question there. It's really too confusing, difficult for me to read and to answer. Yeah, so I want you to contact me by email. That's the point. Okay, good. So see you next time then.